Hello and welcome to video 51. Again to my students. I apologize for not being there, but hopefully it's better than not having somebody explain it. What I want to talk about is the fact that when you take charges and you put them near one another, they either attract or repel one another, which means you're either going to have to add or remove energy to make that happen. How much energy? That's what we're going to talk about. So in order to envision this, so these are going to be the same four charges we did in video 50. You have to imagine that this is a universe where these charges are the only charges in the universe. I know it's a little self-centered, but that's the only way you can do this. And if other charges are really far away, it's so small of a difference that you can't even tell. So the first rule is going to be that when you add one charge, and there are no other charges in the universe, you didn't have to push against any other electrostatic forces. So you didn't do any work. You didn't gain or lose energy in the system. But every other time you go to put charges in, you're going to have to do work. So if I take some other charge and I bring it in from infinity to here, it's going to bask in the electric field that comes from this first charge. And in doing so, you're going to have to apply a force against the force due to the electric field from the first charge. So that's one work that you're going to have to do. That's some change in potential energy. If I then go ahead and bring in a third charge from infinity, and I bring that there, it now is experiencing a force from both charge A and charge B. So charge C, what I do is actually calculate the work required to bring it in against A and the work required to bring it in against B. And then, as you can imagine, when we bring in the fourth, there are going to be three terms because you have to calculate the work done against A, against B, and against C. So let's take a look at this problem. What I'm going to do is I'm going to redraw this. Maybe make this not quite so zoomed in. And these four charges are still going to be 2 units apart. So this is still going to be charge A, still going to be charge B, still going to be charge C, and still going to be charge D. A has a charge of plus 3 coulombs. B has a charge of minus 2 coulombs. C has a charge of plus 6 coulombs. And D has a charge of minus 4 coulombs. When we look at the sides, I'm going to use black instead. The sides of this square are still each 2 meters, 2 meters, 2 meters, and 2 meters, which is going to mean the distance across the diagonal, being that this is 45 degrees, special triangle, 1, 1, radical 2, or 2, 2, 2, radical 2. When we bring each charge in, we're going to have to do some work. So the first charge that I bring in A, there is no other charge in the universe, so there was no additional work. However, I'm then going to have to bring in charge B, and charge B is going to have to do some you're going to have to do some work on charge B. So the work on charge B due to A when you just bring in B. So in other words, A is for free, and then when you bring in B, you're going to have to do some work because B experiences an electric field due to A. Now keep in mind that work equals Q, the charge, times the electric potential. In other words, if you want to bring some charge Q in from infinity, you're going to have to multiply that charge times the electric potential that exists at that location. And we're going to do these one at a time. Remember from the previous video 50 that the electric potential due to a single point charge is K Q over the distance. So in this case, if we're going to figure out the work done on B in the due to the electric field of A, the work on B due to A is going to be equal to Q B, because that's the charge that we're bringing in, times the electric field due to A, which is going to be K Q A, over the distance from B to A or A to B, however you look at it. Again, this is a scalar, so you don't have to worry about direction. That makes it a lot nicer. Now, in terms of terms, let's rewrite this here to give ourselves some room. So the total work, at first you're going to bring in A, that's for free. Then you're going to bring in B, and you're going to have to calculate the work done on B by the electric field from A. No big deal. Then you bring in C, and there are two other charges existing, so you're going to have two terms. You're going to have to do the work due to the fact that there's an electric field from A, so the work on C due to A, and there's going to be work you have to do due to the electric field from B, so that's going to be the work on C due to B. Now, you can see how this grows. If you have charge D, well, when you bring in charge D, there's a work as you bring in charge D due to the electric field from A. There's going to be another term, the work bringing D in due to the electric field from B, and the work on D due to the electric field from C. So if I go to actually write out these terms, I'm going to skip a step in that, remember, work equals K, Q, whatever the first one is, times Q, whatever the second one is, times the distance between them. Every one of these terms is going to have K. So I'm just going to go ahead and I'm just going to pull that out on the side. It's going to make the math a little bit easier. So this is going to be QB times QA over the distance between B and A plus QC times QA over the distance between C and A, etc. All the way until you get to this last one is going to be QD QC over the distance between D and C, like that. And I'm not going to write all those out because I think you can follow that pattern. I'm just going to skip right to the numbers. So when you look at QB, it's going to have a value of minus 2. So let me just put up just a little so you can see the picture. Minus 2. So that's minus 2 coulombs times, for A, plus 3 coulombs over the distance between those two is going to be 2 meters. Plus, for C and A, that's going to be plus 6 for C, and A is going to be plus 3 over the distance between C and A is 2 meters. Now we're going to do between C and B. C's got a charge of plus 6. B has a charge of minus 2. Don't forget the minus. And the distance between these is 2 square root of 2. Now we're up to term dA. So now as you bring this one in, we're going to have to calculate the work done due to A. The charges are going to be minus 4 and plus 3 coulombs. Sorry, I'm leaving off the units. It just makes it a little less cluttered. The distance is the diagonal here between A and D, and that is also going to be 2 square root of 2. And then we've got to do between D and B, which is going to be minus 4 times minus 2 over, that distance is 2. And then the last term is going to be between D and C, and those two charges are minus 4 and plus 6 over the distance 2. And when you plug all of that in, what you wind up with is you wind up with negative 18.97 K is going to be the total work that is done. So if you go ahead and you plug in the value of K, we'll just use 9 times 10 to the 9th newtons meters squared per coulomb squared. You're going to get a total work that is negative 170.7 times 10 to the 9th joules. Now, granted, that is a really big number, but the reason that's a really big number is the charges we chose to put there, whole coulombs, 3 coulombs, 2 coulombs, those are huge charges. But reviewing the steps here, calculating, whenever you bring charges together, you need to do some work. The reason is the first charge that's there has an electric field. To bring another charge in, you're then going to have to apply a force against that electric field. So it's going to require some work, either positive or negative. So what you do is you go through this step by step. For every one charge, you then go figure out the work that's required from each of the previously existing charges. So charge A gets there for free. Then charge B, you have to figure out the work done due to the fact that there was a charge A there. Then you bring in charge C. You have to figure out the work that was done due to the fact that there was an A and there was a B there already. And then you bring in a fourth charge, and you have to figure out the work done due to the fact that there was an A, due to the fact that there was a B, and due to the fact that there was a C. The reason you do work is the fact that the work is Q times the electric potential due to that other charge. Electric potential from a point charge is KQ over R, and then you have to multiply to get the work by the charge that you're actually bringing in there. Again, much like in video 50, you're dealing with scalars here, significantly easier because you don't have to figure out components. But you just have to do this very systematically, very step by step. I recommend you practice with this. And this works whether you have 2 charges you're bringing together or whether you've got 1,000. Clearly 1,000 is a lot of work, but I thought 4 was sort of an in-between number that had a number of steps that you can follow, but wasn't too overwhelming. So I hope that this helps you. I don't know if this helps you more or less than if I was in class today, but this is something you definitely want to make sure you're able to do, and hopefully you found this helpful.